Hi folks, little three-headed monster here, energy, work, and power. First of all, let's start with these two, energy and work. Let's start with that. Work, by definition, is a change in energy. All right, that's given to you in the reference table, but it's a darn good concept to have in your mind. I'm going to start talking about work, and one way we calculate it is that, which means that work measured in joules can be measured in or is equivalent to uh, the Newton meter. A joule is a Newton meter. And what you should know from before is that a Newton is a kilogram meter per second squared, well, times that meter. So a joule, it wouldn't hurt you to know both of these, what a joule is. All right, not the rarest thing in the world to be asked that. Okay. Remember, for work, if we're talking about force and displacement, make sure we're using a component of force that's parallel to D, because we say that work is done when force causes motion. So in a case like this, dude holds box, no work done. Dude holds box and walks this way, no work done. Dude lifts box up, yep, work done. No work, no work, work. All right, we have a force upward and an upward displacement. Yep, that guy does work. Okay. Now, energy, notice that since energy is really a lot like work is just a change in energy, all energies are also measured in joules. All right, so works and energies all measured in joules. And the kind of most common scenario, and maybe the most challenging sort of thing to do is one of these where you have to do a conservation of mechanical energy. That's a G. All right. So that's, there's three big scenarios where you should look to do that. One is the pendulum that swings back and forth. Two is, two, I don't know, maybe it would be something like this. Something's moving at a certain speed there and a faster speed here. It could be as simple as something just sliding down a hill. Oops. Can I move over here? Sure. Okay. So in a case like this, we'd start with that idea, right? Mechanical energy. In this case, there's only two forms of mechanical energy. Gravitational potential energy, initial, and kinetic energy, and then PE final, and KE final. And this turns into mgh initial plus 1/2 mv initial squared, mgh final plus 1/2 mv final squared. I would recommend, really recommend, in any problem like this, start with that. What we get in trouble sometimes when people will just write like PE equals KE. Be careful with that. All right, so take the extra 16 or 17 seconds, write this out, and figure out what goes away. All right. In many cases, it'll either be that it's all initial gravitational potential energy and that turns into all final kinetic energy, or it might be that all initial kinetic energy turns into all final potential energy. All right. But I would start, like I said, start here and then cross out anything that goes away. Okay, those are three big scenarios: pendulum, roller coaster, something sliding down a frictionless, probably hill. All right, um, um, those are three good conservation of mechanical energy situations. Okay, um, but the big deal, this is something that you might see, right? You might see something like this: energy versus time. That what they want you to see is that energy stays constant, right? There's no change in total energy over time. Okay? One thing you might see is in a situation like this, if this is not frictionless, then we'd have some initial mechanical energy and then some final mechanical energy. Well, what will happen here is that if this is not frictionless, then initial mechanical energy will not be equal to final mechanical energy. All right? Because let's say this thing was at rest up top here. Well, its gravitational potential energy does not turn into all kinetic energy because of friction. All right? So this can lead to a change in internal energy. And we call that's referred to in the reference table as Q. So what we might have here is some big amount of initial mechanical energy and some smaller amount of final mechanical energy, but some additional internal energy, right? Because surfaces heat up due to friction. All right, so let's say, for example, that in the beginning you figure out that there are 100 joules of mechanical energy. Well, based on, say, maybe the speed at the end, you figure out, well, gee, now there are only 90 joules of mechanical energy. Well, that must mean that the object had an increase in internal energy of 10 joules, because now we're not just saying that mechanical energy is conserved, we're saying that plain old energy is conserved of all forms. Okay? What they don't say, they talk about internal. What they don't account for is, sure, there's some sound energy that's created, but we don't have a great way to quantify that. Okay, so they'll just capture any lost mechanical energy as internal energy. Okay? What else in energy? I think that's a pretty good little stab at that. Now, for power, all you have to really understand is what power is. Power, by definition, is the rate at which work is done. All right, well, we know that work can be expressed as F times D, and here you'll see that D over T is this. So this is one that the Regents exam, lots of exams, like to use. They like to see if you can get to that understanding there, that power can be the product of force and velocity. All right, so in some cases, like we'll say lifting a mass at something about a constant speed. Well, let's see, like a motor, like is attached to this thing. Here's this motor. What is that? It's a motor somehow. I don't know. And it's lifting this mass up. Well, what this thing would have to do is apply a force that's equal to mg, right? And if they tell you how fast this thing moves, you would say, well, the power is the force times velocity. I'd use mg and the velocity. So that's a pretty common, tougher kind of problem. Okay? As I hope you know, well, this means that power is measured in, well, joules per second. Well, that's what we call a watt. All right? A watt. So a watt this over again, is a joule per second. Okay. They will also sometimes ask you to rearrange this, and as we know, remember that work is a change in energy. So sometimes they'll say, how much energy is required to do something. So I'll just write that. How much energy required or expended or blah, 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 blah. In many cases, what they're asking you to do there is really look for the amount of work done. So that amount of work would be power times time. All right. Once in a while, you'll see that. Okay, but shouldn't be too crazy with power stuff. Okay. Adios. Adios.